All right, part 2 of the fundamental theorem of calculus. If f is continuous on the interval, and that's important again, then our integral, as we find the amount of area from a to b, ends up being the antiderivative of at b minus the antiderivative at a, where we saw that that is true, that's the antiderivative because the derivative of the antiderivative equals that function that we're taking the area under. So some applications of this: if you're asked to evaluate a definite integral, we're looking for what is the antiderivative of the function listed here. Well, here our function is 1 over x, so we're thinking what function has a derivative that's 1 over x? It's natural log. So then this would be the natural log of x evaluated at both 6 and 3. With antiderivative, it does end up being absolute value of x here because the way it's graphed, the graph of 1 over x looks like this. So it doesn't matter if we're over on this positive side, but in order to be able to find the area if it were negative, we need that absolute value because you can't take natural log of negative numbers. Okay, so now you plug those values in, so it'd be natural log of 6 minus what we get when we do natural log of 3, because that's the antiderivative at b minus the antiderivative at a. Going through and evaluating then, neither of these natural log 6 or natural log 3 evaluates nicely, but oftentimes what you're going to see on the test is that they will simplify this by using log properties. So whenever you have the same type of logs being subtracted, we know that's the same as the natural log of the first thing divided by the second thing. So the simplified answer here is that this would be the natural log of 2, or the exact value would be natural log of 2. One thing to be careful of when applying this, it says what is wrong with the following. Well, let's go through and kind of see here. We're trying to find what's the integral of from negative 1 to 3 of 1 over x squared. Well, it looks like they rewrote 1 over x squared as x to the negative 2. That's perfectly fine. Looks like next step they found antiderivative, and it looks like it's the right move here. Remember, we add 1 to the exponent, and then we put the reciprocal out front, so nothing. That looks like the correct antiderivative. Now we would plug in both of these values, and recall we could also write this as negative 1 over x from 3 to 1. So does that follow correctly here? Looks like if we plug in 3, we would get negative 1/3 minus what we would get when we plug in, sorry, this should be a negative 1, minus what we get when we plug in negative 1. So if we put negative 1 in there, that would come out to be minus negative 1 or plus. So we're minusing the positive value. That looks correct. And negative 1/3 minus 1 is negative 4/3. So why are they saying this is incorrect? Well, this is the incorrect answer. It's not that they did anything wrong on this calculation. It has to do with the application in this case. Remember back here, what did we say has to be true in order to apply this? You have to be continuous on A to B. If we go back to the problem we are just looking at here, that is not true. 1 over x squared, the graph of that is not continuous at x equals 0. That's not in the domain there. We get dividing by 0. On the interval from negative 1 to 3 here, are we passing through x equals 0? Yeah, we are. This graph has some kind of asymptote there. This is not going to give the correct value because of that. So you have to make sure that you are continuous. Otherwise, even though it looks like we got a correct answer, it's incorrect because this is not continuous. Later we'll look at how you can possibly find the value of this, but it does not come out to be negative 4/3. In fact, it's going to be some kind of positive value, because if you graph this, the graph looks something like this. So we should have some kind of positive answer. It may be that there's infinite area here, but it's definitely not negative 4/3.